Good morning to everybody. Sorry for not being there, but as a professor at the uni, I'm fully duty with my teaching in this period, so I cannot say no to my students. And okay, so as I was asked to present our digital tools, is also the aim of the today's events. I'm gonna show you what, as UCSC and CityMat, we have partly developed as digital tools to support the MRV within the carbon farming, let's say, topic. Of course, everything cannot be done in 3 years, as you can imagine, in a project. So it's mostly done the soil carbon model in part in the farms for climate, but some components of our modeling OPC, let's say operational processing, is also being developed in other projects. But here in Clean Farm, we really packed all the components in a not ready to market digital tool, of course, but in something that in the future can be used by private companies in the real carbon farming project under the carbon removal certification framework regulation. So it's the EU regulation that has been approved, and in this year, just to give you let's say a political background, we will be published the delegated acts with all the rules for the research center, for the private companies, how to use the models to monitor, report, and verify. So after this introduction, let's dive into the remote sea. Remote sea simply because we leverage some soil carbon model, and our central model is rock sea model, but we leverage a lot to reduce, let's say, the data entry burden, because most of the times to be scalable and to apply at real carbon farming scale is not just a simple model and exercise on the field that you show here, that you see here in the slides in the background, but it matters a lot, the scalability and the automatization of data input. So remote sea, because most of the data inputs for our soil carbon model comes from the satellite and comes from a kind of semi-automatic way. Flexible, because we need to be flexible in our domain, because we cannot think that all the agri-food industry that are going to incentivize the adoption of these practices are tempted to say, let's adopt only these and these practices, because our modeling should be calibrated and validated for a series of carbon farming practices, okay? And as you see here, I always like this sentence from a famous US scientist: you cannot manage, or better, monetize what you do not measure, okay? Even if we realize that our carbon farming potential is very low, but at least we have measured it. Okay, so I've already introduced where we are. We are in Northern Italy, and especially in Europe, and Europe wants to be one of the first continent climate neutral, and to reach this climate neutrality, although I do not fully believe that is technically feasible as society, but by the way, also agriculture can do something toward this direction. And the carbon removal certificates is the units that can be used for offset or inset. But we have rules. One of the rules that the program, so a group of farmers enrolled by a project developer, they adopt one or more carbon farming practices. Altogether, the project developer, with an MRV, with an operational processing chain to monitor, report, and verify these benefits. And which are the benefits? Translated into the monetary terms in a carbon exchangeable units. So is basically a credit, is a benefit in terms of temporary net carbon removal in the soil. Net, because is a difference between the carbon removal in the carbon farming project, CF you see below, minus the carbon removal of the baseline. And here I come directly into the topic of baseline. We have to be able, with our OPC, to be accurate also to provide a measure of the carbon removal in the baseline. So the business as usual, what they do normally do, because each unit that we provide needs to be verified against models and ground truthing measurements, but also has to be additional from a climate and financial and legal point of view. And additional to what? To what is already being done. That's the baseline. So that's the carbon removal certificate minus, and that's why we don't have to forget that we are not fully done just by measuring and modeling the carbon removal in the soils. Also, we have to check if to sequester this amount of carbon in the soil, like in the right picture you see here, cover crop field, we must be able also to provide if we did have an increase in the greenhouse gases associated to the adoption of these practices. Because if we adopt cover crops, instead of leaving bare soil, we spend and consume gasoline. So we emit CO2, and we probably emit a bit of N2Os from this soil to get the cover crops done and cultivated, okay? So we have in case to subtract any additional greenhouse gases. And this is normally done adopting an LCA approach. Okay, but let's enter on the challenge on measuring and sampling carbon removals. Carbon removal is a difference of carbon stock in the soil between not only, a time frame, but also compared to a baseline plots. But simply talking about a field, this is one of the field of our living lab. We started a few years ago, and the challenge was simple. I mean, it's well known by all the soil carbon scientists, but in general by all the modelers. Sampling and measuring carbon removals in stock is tough. Let's take, and as we did, 10 random samples within each of these grids. And this is the carbon concentration variation, even not the carbon stock, just the carbon concentration variation, these 0.3 hectare cell grids. We do it also for all the other cells, and that's the picture. That's the initial soil carbon variability of one of our field. This is the translated, sample taken in a digital soil map. And this is the variability, which is the soil carbon stock. We have on average 55 tons, plus minus 4. So it's already a lot of variability. But what's then the potential to sequester carbon? That's, of course, an average carbon sequestration rate for our pedoclimatic condition and for the practices that are technically and economically feasible to be adopted. That's the range from 0.3 to 1 tons of carbon per hectare per year. What does it mean? That in most of the cases, if we do have thousands of hectares, so a lot of hundreds of fields, in most 99% of the field, the stock variability of the field, so the spatial variability, is higher than the technical carbon sequestration rate. And that's a challenge. This means, and this leads to one of the first conclusions that we come, not just in the Farms for Climate project, but also in other projects where we are working for carbon farming related things, is the measure and remeasure approach is not economically feasible from a cost-efficient point of view. Because if we do want to monitor, report, and verify carbon removal just by measuring with soil sampling at the beginning and remeasure at the end of a 5-year accrediting program, because the minimum is 5 years, and I do think, I'm pretty sure that most of the carbon farming projects, they will start lasting for only 5 years. In 5 years, you have to be able to detect in a soil sample a variation of only 0.01%. That's much, much lower than the detection limit. But we have also good news in our region. We are very silty clay soils, so it means a lot of carbon sequestration capacity. So we are far away from the carbon saturation. So this, for example, the carbon sequestration gap that we do have in a field. So 30 tons means a lot of spaces to sequester carbon with many, many different carbon farming practices. But then we come into the real things, because there are many research centers, many projects that they do talk, probably too much from my point of view, about carbon farming, but they probably don't know what is MRV. MRV means having a model, because as I said, I challenge very much, I would like to see very much with facts the ability to detect carbon removals with measure and remeasure approach. So let's assume that is not feasible. So let's enter on the modeling. So hybrid sampling at the beginning, modeling what's going on in terms of carbon removal with whatever approach, soil carbon model, ecosystem model, with or without assimilation of remote sensing. Okay, that's the standard procedure. But we have to choose a model, a modeling workflow, and especially not only the modeling workflow, but especially what? What we do call model domain. Okay? So model domain is so the model is chosen, the model is tested and assessed if its performance in the new domain is sufficient. But which is the domain? Pedoclimatic conditions, carbon farming practices, and crop types. We have to be sure that we are in the green shape, in the green arrows. So our model and its uncertainty analysis is calibrated for that domain. If the performance is good, it can be used for project modeling. Okay? But this has to be done by research units, by the research center, because they have the scientific, knowledge to calibrate, validate, and independently verify within their domain of validity of a model. The standardized way is part of also of one of our deliverables, but then we have to be able to separate the research units that do calibrate and validate and cross-validate, plus they are able to propagate the uncertainty of our model estimate, and then there will be private companies that they will try to automatize this modeling approach and to offer this as a digital solution to the private companies. So the project developer can use in a simplified, user-friendly version this model to do their modeling. But then at the end, the research unit comes back again to add them to select the points, the sampling point to verify, the model estimates. What does it mean? Then monetizing carbon removals. As I said, it's not just about the carbon farming practices and their ability to sequester carbon in reality. It's the ability to be able to work within the so-called margin of error. Because let's imagine that our model has this kind of errors in simulating the dynamics of soil organic carbon. Okay, starting from a cover crops, one of the most debated carbon farming practices, but on our pedoclimatic condition, cover crops, they do have this carbon sequestration potential. So 300 kilograms of carbon net sequester per hectare per year. So if we do adopt in all the fields of our program, but let's keep it the idea to 1 hectare basis. Okay, in 5 years, we are able to sequester 1.5 tons. But if we do have this margin of error to monitor, to simulate, the carbon stock changes, we are not able. Okay, so within margin of error means to be accurate enough. And accurate means that your model is independently calibrated and validated, not on the fields of the projects. So we have to decrease, the margin of errors. But how to do it? We need more digital and spatially explicit technologies. In our case, for example, smart soil sampling. We identify the minimum number, but representative number of samples to initialize soil carbon model. We need to use, because we are in a situation, economic situation for our value chain, that the proximal soil sensor can be used. But we need calibrated and validated models, as I said, and to reduce the data entry burden of, farm activity data, we need also not just for the farm activity data, also for the yield of the crops, because we need to know how much carbon input is entering into the soil. We need definitely to assimilate as much as possible calibrated and validated remote sensing products for many, many other reasons. If we do so, we can start monetizing better within the margin of error our carbon certificates. But, and now I'm taking the cap as agronomists and farmers, we do have to sequester more carbon, not just for be paid back, because if we do sequester a lot of carbon, means adopting the so-called carbon farming done right. So we do also increase the soil organic matter, but to do that, we need to really apply only the practices that are really able in the short term to increase the soil carbon. Okay, because if we do so, we are in this situation. Even if we are not so precise and accurate, we can for sure work with the margin of error to verify and monetize the carbon removals. But, as I said, we need to be additional compared to a baseline. And if our baseline is super standardized and is not representative of the real carbon removals under the baseline scenarios, we for sure fall within the, the risk of over-crediting or under-crediting many farmers, okay? So we are not ethically, let's say, right to really incentivize what's really is the additionality of the carbon farming project. So let's imagine that the pre-project reference 5 years, that's our model estimates for baseline. So we need then to apply this baseline in the calculation ex ante, okay? If you adopt these practices, you can likely sequester 4 tons, okay? That's the credits that you can generate, 3 plus minus 1, because it is avoided one loss of 1 ton of carbon. But then in the reality, you adopt practices over a certain period and over a certain area. So you need then to redo the baseline. Okay, during the project time, you need then to have accurate dynamic regional baseline, because then you have to redo the baseline and also you have to redo the real ex post calculation during the project time of your carbon removal. But if you are not able to do so, you have to assume during the project time the pre-project reference baseline, and that's a risk. If it's not done very well, the standardized baseline, you can really penalize many farmers to be paid. So let's enter then after this introduction, because this was essential to understand why we need to work very well on the calibration and validation of our model, because that should be our objective, you see, the reality. And also, this is an example for soil sampling, because here is not just a matter of soil sampling, but it's also a matter to catch the real variability, spatial and temporal variability of carbon removal. So that the challenge of data input and output spatialization is fundamental, because if I do apply from the beginning, for example, a composite soil sampling strategy, I have only 2 data, one stock value for the lighter part of these fields or for the project, and one for the darker area. So just 2 data. If I have digital tools and if I can use spatialized, very accurate data input, I can also propagate the error that I have on estimating the soil properties or the carbon removal dynamics at a fine scale. And then I have the number to say which is the real net carbon removal. So that's why it's very much important to work both for data input, spatialization, but also and error propagation, because of course, as soon as we add different data inputs in our model, we can also enter and propagate higher errors. Because that's the reality. At what scale do we need to be able to do monitoring, reporting, verification of carbon removal for a real carbon farming program? That's, for example, a carbon farming program that was thought within the Living Lab, and probably in the next year, they will start really adopting, try to be certified under the CRCF, the carbon removal on these farms. 8 farms where they just use 30% of their agricultural land. It means more than 1,000 hectares with 5 crops into rotation and more than 100 fields to be monitored. And for each field, you need some data input. But from a scientific point of view, the challenge is to monitor and report and verify, thanks to the modeling, across 9 soil types, 5 textural classes, and a very different starting stock values. This means that from a scientific point of view, our model needs to be calibrated and validated for this pedoclimatic condition and for the practices that they are going to adopt. Okay, so let's enter then technically into our approach. In our digital platform that we start to design, of course, we don't have the time within the 3 years project to do it, but we will do it. Let's see with which funds. We are trying to not only to cover the ex post, so the model that, you know, in this field is able to monitor the carbon removal, but also to be able to configure the carbon farming program, to do the farm enrollment, to do the field eligibility and also especially the ex-ante assessment, because in front of an ex-ante assessment, you can really see with numbers the real carbon farming potential of a project at scale. And then we will be able to do the smart soil sampling and mapping, the practice monitoring, of course, with the contribution of remote sensing, the verification of practice adoption, with, of course, farmer declaration and other remote sensing base or regional tools like the one that are used for the common agricultural policies, and then the impact measurements and the uncertainty plus the certificates calculation for the reporting and verification to be able that the certification bodies is able to assess the data and the methodology and to verify and give the stamp, and then so the credits and the units can be emitted. But okay, so let's enter on what is the first step of our journey into the MRV. We start using the remote sensing to check if with the machine learning we can have some standardized baseline from remote sensing for the SOC changes over a region. We are lucky in our region, as you see in the top right, we had access to more than 40,000, we are around 60 in reality, 60,000 samples over the space and time, with which we could train and validate a machine learning based algorithm to detect from satellites, the topsoil, of course, not the entire soil, but at least to see what happened in the past 20 years for each parcel of our region in terms of soil organic carbon. I don't want to enter on the technicalities. It's based on a bare soil masking. So we do extract bare soil, we apply our train and validate algorithm, and we can track over space and time the dynamics of soil organic carbon. That's an image that we have produced for Piacenza. But most importantly, I skip this, which type of satellite imagery we use for training and validating, but that's the fact. We can attribute the delta SOC changes to a kind of standardized practice. In our case, we use the farmer crop declaration for each parcel of the region for the last 15 years, and we could use a general additive model to make a partial effect analysis. So to understand which crop rotation is increasing or not the soil organic carbon. So that's already a standardized baseline. And that's, for example, for the main 6-7 crop rotation that we do have in our region. And you see very huge variation, but in general, for example, for the tomato cereals or for the alfalfa, very two contrasting crop rotation in terms of carbon removal potential, you do see which is the delta SOC over the last 10 or 12 or 8 years, okay? And then these numbers, very simple numbers, but at least they do say which is the baseline. So alfalfa is already sequestering carbon. Instead, if you do take, I don't know, tomato cereals, you're losing 0.26 tons of carbon per hectare per year, okay? Then I skip. And then, okay, but we realized that we cannot rely 100% on satellites, but at least we had an idea. Then we have to model each parcel with a soil carbon model. And that's why Remote C comes in within the Farms for Climate project. We have written in R a package to run an updated version of the ROT-C model from Rotanstedt. Updated because we are able to explicitly simulate the fate into the soil and then the carbon sequestration of exogenous organic matter for different organic amendments, but especially for plant residues, okay? And for this, we are going to finish the calibration, the Bayesian calibration of this ROT-C model. But then we start including and assimilating as plant material carbon input, so the plant carbon input, also some AO, Earth observation, so remote sensing products. With remote sensing, we do detect the start of the season and end of the season and the peak of the season of each crops. So we do detect the phenology, and within this temporal window, we are able to use some satellites vegetational index to identify one key factor of the biomass accumulation of each crop, so the fraction of photosynthetically active radiation. Using this information and meteorological data, we are able to determine thanks to the light use efficiency crop model, it's a very simplified crop model solution, we're able to determine the daily and then the cumulative accumulation of above ground dry biomass and then convert it into harvestable yields. This is super fundamental for us because we need to know how much carbon has been produced. So this is the net primary productivity. And with a simple allometric approach, we do fractionate the carbon photosynthesized into carbon input from the roots, carbon input from the roots exudates, and carbon input from the residues. Thanks also to some not yet mature remote sensing product, we are able to detect the permanence of crop residues into the field and then identify when exactly, and here we are on the, we are going back to the bottom right, the residues incorporation day, okay? We do have to know when the residues of crop are incorporated into the model. And of course, to the model, we have also to tell how much type, quantity, and timing of organic amendment. For the moment, we don't have yet an automatized procedure. We're using a manual allocation model that we are trying to develop using the statistics. And this is for the standardized baseline, plus something that we are doing very recently in terms of tillage rate modifier. So we are keeping also the rate modifier part. Sorry if I'm talking too much technical, but this is to be able to use this rate modifier to simulate better the effect of different tillage practice like no tillage or minimum tillage compared to the conventional tillage, the effect on the soil organic carbon accumulation. Okay, for the moment, for the standardized baseline, because it's quite complicated this part, but basically what we are trying to do, I don't know, for sure not by the end of the project, but after the project, we probably in 1 year and a half, we will be able to finish this procedure. So basically, we want to do the spin-up, the historical spin-up of each parcel, because we have the historical land use map of the century, to arrive to initialize to the actual soil organic carbon values for a certain given year, thanks to this ensemble of the Emilia-Romagna digital soil maps and the remote sensing dynamic model. We want then to initialize the stock pool for each agroecological zone. So agroecological zone, for the moment, we don't want to run a specific parcel-specific simulation, but we do want to somehow classify an agroecological zone in terms of main crop rotation. So we did the land information parcel system analysis. So we did classify the main crop rotation, so the most 3 frequent crop rotation within an agroecological zone. Within this, we ran for each parcel the light use efficiency model with which we could have a database of the past 5 years, and we are training a machine learning model thanks to the inclusion of a method generator to have a very dynamic database for simulation. So, and the machine learning model using the meteorological data and the real yields of each parcel, we can really attribute the yield to each agroecological zone to run our standardized baseline. Then the exogenous organic matter, the residue, and the tillage for the moment are going to be used with statistics, but we will be equipped with some remote sensing products, especially in terms of residues and tillage detection. Using the certain number of pixels of sock stock within each agroecological zone, we can then run single and blended baseline. And by blended baseline, I mean incorporating all the potential crop rotation for each agroecological zone. So we have really the real standardized baseline for an area. And we can have really the mean, so the blended baseline. Just an example done for our province, Piacenza. So that's the 2 main crop rotation, like wheat and tomato, wheat, maize, and tomato. We identified all crops into rotation thanks to the LIPS data. And then these are the conventional practices, so no residues incorporation and conventional tillage. And for the last 5 years, for the main 3 soil types, we have this simulated baseline, so standardized baseline. And that's the baseline value, so the delta SOC change over the past 5 years. So you see very different. We are always losing, because nothing to say that we are losing with conventional agriculture in our region, and that's our the statistics. Or better, this is just a simulation that we launched yesterday, and we got the simulation, the results this early morning. For all we classify the region in 4 soil organic matter classes, from low soil organic matter to high level of soil organic matter, for the main 3 soil types. So silty clay in red, loamy in blue, and green sandy loam. And we have run the baseline plus with only single carbon farming practices, just to show the real carbon farming potential with straw return. And where in the territory we do have a possibility to switch or to increase or to conserve to avoid soil carbon loss. And you see, with just one practice is not enough, because in most of the parcel of the region, also starting incorporating, so returning to the soil, the wheat straw is not even able. So we are avoiding soil carbon losses, but not still really sequestering carbon. So that's just a message to many policymakers that they do think with one short practice, you can really do get and reach the neutrality. That's not true at all. So we really need to work also from the agronomy side of the carbon farming. Okay, so ex post. We do select some fields. We do say, okay, in these fields, we are going to adopt this and this practice, and we start monitoring what's going on with the same approach. ROTC again. We do select some sampling points to initialize our carbon model over a territory, thanks to the combination of proximal sensor and remote sensing data to identify with a smart sampling approach where to sample. Then we start monitoring everything for what is possible from the satellites. We do integrate also the field notebooks, so what is normally by law declared by each farmer in terms of crop declare and fertilization. We do estimate the cover factor, I forgot to mention before, in terms of fraction of vegetation cover and fraction of soil covered by residues, because these are important input data for the ROTC model, and when the soil is bare soil, and this is done by satellites. We estimate with the light use efficiency model the harvestable yields and the plant biomass. We do convert into specialized plant carbon input data that is feeding the soil carbon model. Also, the residues are partly detected and quantified by satellites, and then we...
Sorry, Andrea, we have just 10 minutes more.
5 minutes, I'm done.
Or less. Nice. Thank you. Sorry.
Welcome. No worry. Then the organic amendments are taken the data from the declaration of the farmers and ingested spatially into the parcels that are being simulated. And that's how it looks like. For example, the first step before starting the simulation, we need to identify where in the field, in the territory, using a cost accuracy curve. So we use soil sampling, a smart soil sampling approach. We do use a stratified systematic random sampling using Sentinel-2 bands as covariates to determine where in a cost-effective way, which is the minimum number, and especially where to take the initial soil sample. That's the super complicated smart soil sampling approach. We do also use soil sensor, where it's cost effective, its use. We do estimate, and I go very fast, in the farm soil climate, we have trained and validated a prediction algorithm using the Veris iScan sensor to, and I go very fast, to get the prediction of SOC stock. That's the root mean square error that we do have using proximal sensors data and also Sentinel-2, because Look at here the prediction model covariates for the soil organic carbon. It's not just AC, red and infrared that are the readings taken from the proximal sensor in the field on the go, but it also embedded into the prediction model, also Sentinel-2 data. The results are very good in terms of accuracy and precision, and we give to the model these inputs. Then we start monitoring. You see here a leaf area index time series data for some crops, where we are able to detect when the crop starts the season and when the crop is harvested. And then, for example, when we have, like here in the right part, like here, let me use a pointer. You see here, we have a peak, so a cover crop detection. So we are also able to detect when and where are the cover crops grown in the territory. Like here, we are able to detect, you see here, start, peak, and end of the season of each crop into rotation. We are also able, not for the moment, but hopefully by the end of the year, thanks to the work in another project, to detect the tillage type. So plowing, so deep tillage versus conservation tillage. And likely, but I'm not sure, by the end of the year, probably it takes more than 1 year also to detect the quantity of residue, especially when, thanks to the use of hyperspectral satellite imagery, but that's for the moment is not yet incorporated into the platform. But then what is already available, thanks to the development of a dedicated air package, the estimation of the biomass. That's
Andrea,
our
can you hear me? Sorry for the interruption.
Yeah.
Yeah, I'm Sam. Hi, how are you?
Thank you. You?
Sorry for the interruption. Just can you go back to the previous slide? Yeah, about the detection of the tillage type.
Yeah.
Yeah, did you get this this kind of detection from the satellite image or from the model itself, remote seed?
No, this is an output of a Sentinel-1 base operational processing chain. We do use Sentinel-1 imageries to detect and classify the tillage events.
Yeah, but my question was about the principle of this kind of detection. I mean,
Yeah, we do use Sentinel-1 images. It's a radar-based satellites, and with which you can really detect the rugosity and the viscosity of the field. So you really detect the change in the soil surface roughness of the fields. And if you use many field observation, you can train a deep learning based model to associate these changes of humidity and roughness to a tillage events. So basically you train a model with field observation. And observed data are the Sentinel-1 V plus and V minus bands.
yeah, okay, thanks.
Other questions?
The lesion of the tillage detections. I cannot see it.
What,
Other
sorry?
questions? Comments?
Okay. Thank you, Andrea. Thank you.
Okay, let me finish and then we can have questions.
Yes.
So basically, the light use efficiency model is a very simplified model where the only remote sensing inputs is the fraction of photosynthetic active radiation estimated from satellites from a simple linear relation between NDVI and NFPAR. And all the other inputs model are coming from the meteorological station, and the actual use efficiency is the sum of products of environmental stressor. Again, temperature or soil humidity stressor, mostly derived from satellites and meteorological data. So we can have the accumulated above ground dry biomass and then the conversion to a harvestable products. I skipped the super complicated data simulation modeling framework for light use efficiency, but that's just to show a real simulation estimates of the carbon inputs. So that's the biomass of the wheat. In the right part, you see wheat, carbon farming plots, and the baseline. Then the cover crops, where we do not have biomass, so it's bare soil, and then we do have biomass, and then maize, and again cover crops. The pixel base, each pixel is entering the soil carbon model. Soil carbon model is then able to, then I skipped, to simulate. These are the first results of 5 of the farms of the Living Lab within Farms for Climate, and these are all the accuracy metrics and precision metric and the accuracy tests following the Verra standards. So you see in both in baseline and in the, in carbon farming here, the model absolute bias is always lower than the pooled mean uncertainty of the all 5 farms. So we are about 30 hectares monitored, and that's the root mean square error of the delta SOC, not of the single time points. We also verify with soil sampling at the end of the 3 years, also to answer one of the open question of Farms of Climate, if it's able or not to verify, you know, and detect carbon removal changes in 3 years. Yes, only if we do met the previous requirements. So calibrated and validated models, very high carbon stocking practices, and final verification. And you see the points here, in only one field, we were outside. So the observed value falls always within the 90% confidence interval of our model estimates. So that's a good starting point for the project developer in the future to use our approach. If we do combine all the data from each field over the 3 years, in this, 15, but it's 30 hectares, we can first quantify the emissions, and to quantify the CO2 equivalent emissions for all the agricultural operations, we are using Cool Farm Tool. It's a worldwide recognized greenhouse gas calculator. And then we do the same, that's in Italian, for the baseline and for the carbon farming, where we were able to detect a minus 4% decrease of greenhouse gases. But most important, with the remote sea, we were able to verify that we have emitted, so we have lost almost 5 tons in 3 years per hectare of CO2 as soil carbon, but we also increase of 5%. So almost 20 tons of CO2 sequestered per hectare over the 3 years. Altogether, they are 330 tons of CO2 removed as KPI for our Living Lab, with a total uncertainty of 18 tons. And that's something very interesting. If we do calculate all of this into net temporary carbon removal certifiable units from the CRCF, so the European Union, it might be that potential, of course, because it's not a real certified carbon program. That's the potential of these practices: cover crops, minimum tillage, residues incorporation, 4.0 agriculture for fertilization, to generate quite nice amount of certifiable units per hectare per year. Thank you so much for your attention.
Thank you so much, dear Andrea.
I have some questions or some comments for your presentation. Overall, superb work, very nice, very comprehensive analysis, and very much impressed with the overall portfolio of work you have been doing, Andrea. Keep it up. Your point about the baseline is very crucial, and I think this is one topic that is overlooked by many living labs. I think it is good that, Andrea, you have raised that, because whatever we do, has it made improvements or not, is a function, is relative to the baseline. So I think baseline analysis will be based on observations, a series of observations, or modeling, or a blended approach. That's very crucial here. Another point I would like to highlight is that we tend to mix up between soil organic carbon and carbon sequestration. I suggest that we stick on to either only soil organic carbon, because there could be soil profiles where the organic carbon can be very high, but it could be a net emitter, so sequestration may not be happening. So I think we have to nail it down. We are not doing carbon sequestration research, in my observation, in this project. Of course, we are saying like that, but none of our observations have soil carbon sequestration observations. If it is to be done, it has to be done with either gas exchange or decovariance based of analysis. But only with soil carbon stocks, we can't quantify soil carbon sequestration. So I think we have to, because there could be some, especially from Europe, when when there is a big team of ICO scientists there, experts there, if they evaluate our report and they find that this mixing up between soil, then we could have some criticism. So I think let's stick on to that. Yeah. With that, I think overall our work is great, and I also encourage Andrea. You already have a wealth of data, be it from modeling or. Please contribute to the database so that the project benefits significantly. I think you can make a great role and a great contribution. Thank you.
Thank you, Jit, for the comment, for the business. I totally agree, because we do have many situations all over Europe where we are already sequestering carbon, and we have to take it into account. Of course, the policy decision is to to incentivize the front runners, to reward them. But that's something that has to be still decided at EU level. Coming back to your comment in terms of net exchange, the carbon budget approach. Of course, I know, because in Marvic project we are running an ecosystem model also to check not just the delta SOC estimated from soil carbon model, but we do also take into account other carbon fluxes to make a real carbon budget approach. Because of course, in the ICOS sites, the CROP21 database, we will run different models, ecosystem models, where we do also take into account other carbon fluxes, okay? And we also verify the delta SOC, because I'm pretty sure that, of course, it's not only about delta SOC, but it's also about the carbon fluxes. So with plant respiration and net ecosystem exchange is really the variable that has to be taken into account. But the fact, again, that the ICOS sites are very nice for this, but in most ICOS sites, we do not have the carbon farming practices tested. So you can really be able to calibrate and validate for your pedoclimatic, for your crops, but then technically speaking, if you start adopting some specific carbon farming practices, these practices are not covered by the ICOS sites.
No, I'm not talking about ICOS sites itself, but technically there is a difference between soil organic carbon and carbon sequestration. That's the only point I have.
Sure, but then if you want to use the model has to be calibrated and validated. You can calibrate your carbon fluxes on MPP, GPP, plant respiration, whatever, using only ICOS sites. But suddenly, in the reality, you start adopting carbon farming practices that are not calibrated with the ICOS sites, because ICOS sites, that are expensive, to cover everything, okay, in terms of practices. And that's why we need to be able at least to give a trend. I know that in some situation, the delta SOC is not merely 100% carbon sequestration, okay? But at least for the cropland, it is. Then you can talk about agroforestry and grassland. That's for sure. I'm totally agree with you that we need net ecosystem exchange. But in a situation where we are historically losing carbon, and if we keep the same crop rotation, and for sure with carbon farming practices, you do not increase the plant yield, for sure you can neglect and say, okay, net ecosystem exchange is the same. Probably is a matter of cover crops, probably, because that's the new crops that you add. But with the albedo remote sensing based products, we can also take this into account. But at least in our case, we are pretty sure that soil carbon model is enough to verify carbon sequestration, soil carbon sequestration. Of course, in other ecosystems where you do have perennial crops or grassland crops, of course, there is much tricky.
Thank you. I just shared some views, that's all.